Alright, so this is example E 4.4. It's example 4.13 in the text. And you can see the figure here. We have this table, and it has three forces on it. And the point at which each of these forces are applied are designated by points A, B, and C. And we know their coordinates. We know the magnitude of the forces, and each force is directed straight down. So the question has two parts. The first part is determine an equivalent force system at the center of the table at point O. And then the second part is determine an equivalent force system that consists of a single force, but then specify the x and y coordinates of that force at the point where the line of action intersects the table. So go ahead and give that a shot, and then come back and we'll go through the problem together. All right, so we're going to use a vector approach for this problem. Part A is actually pretty easy. We're just going to find the resultant force associated with these three forces, and that would be applied at O. And then we'll also find the sum of the moments associated with these three forces, and that moment would also be applied at O. The second part is a little harder because we're going to, again, find the resultant force of the three forces, but now we have to apply it at a location where it gives the same moment that we found in part A. So we'll have to find the coordinates of that point of application such that we get the same moment. And we'll set that one up as a multi-dimensional optimization problem, just because that's what we were just talking about. So if we go through the equations, so now we know the coordinates of each of the forces. So we know A, B, and C. We know point O, we're going to call that 0, 0. And so now we can find position vectors from the center, from O, to each of those points. So ROA, ROB, and ROC. And then we know also the forces. We know their magnitudes and direction. They're all in the minus J direction. So we can go ahead and specify each of the forces. And then the resultant of the forces is just the sum of those forces, the vector sum of those forces. And the net moment that these forces provide about point O is just the vector sum of the moments that you get from each force alone. So ROA cross FA plus ROB cross FB plus ROC cross FC. So doing the computations is not very hard, right? We'll put the coordinates into E's. We'll put in the magnitudes. We will then specify the forces based on their magnitudes and the direction. And then finally, we'll go ahead and compute the position vectors between the points of application and the center. And here at the very end, I'll make the vector sum of the forces is the resultant force, and the vector sum of the moments, which is just the cross product of the position vectors and the forces, is the vector moment. If I solve, I get minus 480 newtons straight down, and I get this moment that has components in the x and y directions, but no component in the z direction. So that tells me that it lies in the plane of the table. And we can actually look at this visually, which is always kind of an instructive thing to do. So if I look at the magnitudes of the forces and the moments and the position vectors, the magnitudes of the forces and the moment are similar, so they should look okay on the same plot. But the position vectors and the coordinates in meters are way too small. So I'm just going to convert them all to millimeters so that the plot looks sort of readable. And then I'll use the dollar vector plot directive to make a plot showing this information. So I'm going to call the plot part A. I'm going to plot the position vectors, ROA, ROB, and ROC in millimeters, and I'll make them black, and I'll have them obviously start at the center of the table. And then I'm going to plot the forces and I will apply the forces. So I'll start them at their point of application, so A, B, and C in millimeters, and I'll make them red. And then finally I will plot the resultant force, and that would be applied at the center of the table, and that'll be red, and the moment also applied at the center of the table, and that'll be purple. And if I run now, I can see this plot, and it makes sense, right? I see these three forces. I see that if I add the forces together, I get the resultant forces. And not only that, I can see that if I take the net moment of those forces, it's trying to rotate about this moment vector, which looks right. And also that the moment vector has no z component, right? Because all the forces were in the z direction. Right, in part B, then, we need to do basically the same thing, except for now we're going to move this force, this resultant force, around until we get it at a location, at a point of application where it gives the same moment, MRO, right? So I'm going to go ahead and make a new tab, because I have the professional version of these here. I can have multiple tabs in my equations window, and this is going to include pretty much everything up to computing the force and the moment. And then I'm going to continue, right? So here I'm going to have a point D on the table where I'm going to apply my force in order to get the same moment. And I know that D is on the table, so I know its Z coordinate is 0. And I don't know its X and Y coordinate. In fact, that's what I'm trying to find, is the X and Y coordinate that gives me that moment. So for now, I'm just going to assume a value of D sub X and D sub Y. And I'll go ahead then and compute the position vector, ROD. And then the moment associated with applying this resultant force at point D around O is the cross product of ROD and FR. And we'll call that MRO calc. And what we would like is for MRO calc to be equal to MRO. So here when I calculate MRO calc, you'll see it's not equal because I didn't choose the right dx and dy. And there's a whole bunch of ways now to close up my problem. Because we just talked about multi-dimensional optimization, we're going to use that, right? So what I'm going to do now is I am going to comment out the d sub x and d sub y coordinates that I applied up here. And I'm going to calculate an error, and the error is just going to be how different is the moment that I calculated, MRO calc, from the moment that I want, which is MRO, right? So MRO calc has an X and a Y component, just like MRO does. And so my error is just going to be the sum of squares of the difference in the X components of these moments and the Y components of these moments. So I'll go ahead and calculate that error. And at this point, I have an optimization problem, right? I would really like to vary d sub x and d sub y, so the location where I'm applying my force, such that this error is minimized. In fact, I'd like it to be 0. So I'll go ahead and select min-max from the calculate menu. I'll set up the optimization problem here so that I am minimizing the error by varying two independent variables, dx and dy. You can pick whichever method here you think is going to work, and they all should work pretty well. And you can solve the problem. And I think what I'm also going to do here, just to visualize the solution, is I'll go ahead and create a vector plot. So same idea, right? I'm going to use millimeters for the position so that the plot looks okay. So just as before, I have position vectors and then these locations A, B, and C. Now I have a position vector ROD and D and point D, so I'll go ahead and add those. And then my vector plot is going to include, so I'll call it part B, and it's going to include ROA, ROB, and ROC in millimeters, right? And I'll make them black. And it's also going to include ROD in millimeters, and I'll make that blue. And those all start at the origin. And then I have FA, FB, and FC, so these are the applied forces, and I'll put them at their locations, again in millimeters. And then I am going to put FR at location D. And so here you can see that FR, after I run here, FR, when it's located at location D here, provides the same net force as the sum of these three forces A, B, and C, but it also provides the same net moment that these three forces did at their application. So basically, if I'm sitting at location O, it feels the same for me to have FR as it does if I have all these individual forces, and it looks right? You can see how it's the same force, and also you can imagine it's about the same twisting moment that you're getting.